Hey engineers, welcome to the Explainer. Today, we're going to roll up our sleeves and refactor the absolute core of transformer architecture, taking it straight from whiteboard math into production-ready PyTorch. Because honestly, if you've ever wondered how modern AI models manage to chew through gigabytes of text without completely choking your servers, well, you're exactly in the right place. We are moving out of the theory and jumping directly into the code base.
Right off the bat, this crucial quote from the Attention is All You Need paper is what changed the landscape entirely. By outright dropping legacy, recurrent, and convolutional neural networks, they completely stripped away the sequential processing bottlenecks and those dreaded vanishing gradients that made older models such a nightmare to scale. It was a massive paradigm shift in systems engineering, and honestly, it eliminated a ton of technical debt.
Okay, here's our roadmap for today. We're going to start with the attention breakthrough and the math behind it. Then we'll analyze why manual Python creates such a massive bottleneck. From there, we refactor into production-ready PyTorch, scale the whole thing up with multi-head attention, and finally, we'll look at the raw power of parallel processing. Let's get right into it.
Section 1. The Attention Breakthrough, dropping RNNs and CNNs.
So the core idea here is pure attention. Instead of processing a sentence sequentially, waiting for step A to completely finish before step B can even start, tokens natively evaluate their relationships with every other token, all at the exact same time. From an architecture standpoint, it's just this incredibly elegant, highly scalable approach to understanding context, completely bypassing the bottleneck of linear execution pipelines.
Section 2. Math of Scaled Dot Product, the Q-K-V formula. Now here is the fundamental equation for scaled dot product attention. As an engineer, you can essentially read this like a pure function. You pass in your query, key, and value matrices. Then you do a matrix multiplication of Q and the transpose of K, scale it down by the square root of your dimension just to keep your gradients nice and stable, apply a softmax for normalization, and finally, multiply by V to get your output.
Translating that math into procedural logic requires 4 very strict operational steps: compute the dot product, scale it, apply softmax, and multiply by the value. Now, sure, it looks simple enough on a whiteboard, but as we all know, how you actually implement this algorithm in software makes all the difference in the world for your servers.
Section 3. The manual Python bottleneck. Educational, but slow. When we look at building this manually, it's highly educational, but painfully slow. Using list comprehensions and standard math library functions for your softmax logic technically works, but it's incredibly sluggish thanks to Python's GIL overhead. And the dot product alternative? Iterating through triple-nested for loops over your arrays. Anyone who cares about production code knows that a triple-nested loop in Python is an absolute big O of n-cubed nightmare. It will completely choke your CPU when you're dealing with the massive dimensional arrays needed for real-world language modeling.
Section 4. PyTorch, production-ready efficiency with tensors and matmul.
Now see the stark contrast when we switch to PyTorch. That blocky, dense, triple-nested loop logic is beautifully replaced by sleek, vectorized one-liners. We literally swap out the loops for torch.matmatchul and f.softmask. What's absolutely crucial here is that PyTorch pushes all these operations down to highly optimized C++ and CUDA running on bare metal. Instead of calculating one dot product sequentially, your GPU just blasts through massive blocks of the matrix simultaneously, leveraging highly optimized memory caching.
As engineers, we literally live and die by tracking exact data shapes, mostly to avoid those nasty runtime errors. Notice how our inputs, our Q, K, and V tensors with shapes of 2x4x8, cleanly map to a 2x4x4 attention weight matrix and then return a matching 2x4x8 output tensor. As long as your dimensional math aligns perfectly, the framework just handles all the complex memory routing and execution scheduling for you.
Section 5. Scaling with multi-head attention. Learning different relationships.
So, to really scale this architecture, we split the workload up. Instead of running one massive attention calculation, we split the embedding dimension into multiple independent heads. Think of it kind of like assigning different specialized developers to review the exact same pull request. One checks for security vulnerabilities, while another is just looking for syntax errors. PyTorch handles this effortlessly via the multi-head attention module, capturing diverse contexts simultaneously and then seamlessly concatenating them all back together. Let's check the specs on this. Passing our tensors through a 4-head setup with an embedding dimension of 16 returns these exact output and weight dimensions.
This really proves the plug-and-play efficiency of the PyTorch implementation. You don't have to manually manage parallel worker threads or deal with the technical debt of synchronizing them. The module abstracts all of that away so you can focus entirely on your high-level system architecture.
Section 6. The power of parallel processing. Assembling the architecture.
Zooming out to the macro level, the transformer encoder block wraps our multi-head attention module with standard components. We've got self-attention, add and layer norm, a feed-forward network, and another layer norm. It creates a highly robust modular block. You can stack 12 or even 96 of these together. Because of the optimized tensor math we just refactored, data flows through them like water through a wide pipe.
So the absolute most crucial takeaway is this. Because we ditched legacy sequential processing, every single token's attention is computed simultaneously. Token n absolutely does not require waiting for token n-1 to finish. It all resolves in one massive matrix multiplication. This is exactly what unlocks the true parallel processing power of modern GPUs, and frankly, it's what makes billion-parameter models an engineering reality.
We've seen a massive leap in efficiency today, going from nested loop bottlenecks to elegant, hardware-accelerated tensor operations. It leaves us with one provocative thought to wrap up this explainer. If dropping sequential logic for pure, parallel mathematical attention completely changed the world of AI, what sequential bottlenecks are still hiding in your own codebase? Thanks for joining me on this code review, guys. Keep optimizing, and I'll catch you next time.